the robotic arm wrist. So here's the robotic arm, here's the camera, this is a figure, and here's the scoop. It's intended to document the samples that are dug up in the scoop. And it could also be used to document areas of the landing site that the SSI couldn't see. And in the event that the SSI actually failed and couldn't provide panoramic imaging, the robotic arm camera rack could also do that. Since it was mounted on this movable platform, it could generate panoramic images that way. Fortunately, we didn't ever have to rely on that. But it was a pretty simple camera, really. It was just a single CCD camera with a double Gauss lens. So this is the camera. You can kind of make out the lens here sitting behind this window. It also had this protective cover that you could rotate down into place while we were digging, so you didn't scratch this beautiful filter window that we had here. The lens inside here, which you can see, it was actually mounted on a focus adjustment mechanism. We could generate 313 different focus positions, and that was required because for imaging things actually inside the scoop, you were relatively close up. And if you were fortunate enough to actually get something interesting right on the edge of the scoop here, we could focus on that and actually have almost microscopic resolution, about 23 microns per pixel. But then we could also focus for things that were far away. To image the entire scoop contents in focus, what's shown here are about 12 different focus motor positions that allows you to image the entire scoop in focus. Now, unlike the SSI, we didn't have filters on this camera, so we couldn't take color images in the normal way on Mars that we take color images. But we had this illumination system of LEDs, red, green, and blue LEDs. So if you were close enough to something and the background illumination wasn't too bright, you could move up and illuminate the sample with the lights and get color information out of it. So to take a color image, you'd do 4 exposures, 1 in red, 1 in green, 1 in blue, and then one without any lamps on at all to subtract your background. In fact, that's how this image was generated right here. This is a color image taken by the right inside the spacecraft while we were flying to Mars. About a month after we launched, we did a checkout of the instruments and made sure that they had all survived the launch and that they were ready for their mission on their way to Mars. And this was taken, luckily, RAC had its own illumination system on board, so it's tucked away inside this biobarrier bag because it's mounted to the robotic arm. And we turned it on and we took 4 pictures and created this color composite. So this is taken in between Earth and Mars. And this is a picture of the scoop. So this is a robotic arm scoop, and you can see the inside of the biobarrier bag right here. So it was a neat picture for me because it proved that this instrument had survived the stresses of launch and looked like we were going to have a good day once we got to land on Mars. The camera, though, it was really pretty old technology. The CCD inside of it was just a 512 by 256 Laurel Fairchild frame transfer CCD. It was pretty old technology. It did have anti-blooming gates on it, though, which was a real advantage, which makes sure or help ensure that you don't saturate your images. The MIR detectors, for some unknown reason, didn't have anti-blooming gates, and so there were a lot of times where we were dealing with the images washing out because we weren't sure of the illumination conditions. But the rack didn't suffer from that because it had these anti-blooming gates that would allow you not to overexpose your images. But it was originally developed for the DISR, which was the Descent Imager and Spectral Radiometer on the Cassini Huygens probe. So this was developed way back in the early 90s. Originally flew in 1997. It was the same detector on the imager for Mars Pathfinder, the same detector we use on Mars Polar Lander. And in fact, the Phoenix optical microscope that's part of the MECA package used the same detector. So it really was pretty old technology, but it still ended up doing its job that we needed it to do. Okay, finally, the final key piece of instrumentation for doing the water observations was the TIGA, or the Thermal and Evolved Gas Analyzer. And this was a new piece of hardware. It was similar in design to the 1999 Mars Polar Lander TIGA, but it was basically built to print from what we had before. So it consists of 8 single-use calorimeter ovens. You can see it being built up right here. These 2 cells don't have the doors on them yet, but there are 4 on each side. And the ovens are located behind these doors. So this is a figure of the oven right here. And these ovens are very small. They're about the size of a pencil tip eraser. So just a small amount of material can go in there. And what the ovens do is they monitor the amount of power required to increase the sample temperature at a constant rate. So that's all it does. It's trying to do these temperature ramps at a constant rate, and it monitors how much power it needs to do that. And so endothermic and exothermic phase transitions can be detected that way. The highest temperature ramp actually goes up to 1800 degrees Fahrenheit. It takes a couple of days to actually get there, but that's how high it can go. And it was intended to be sensitive to water, so this was our main instrument for detecting water, particularly if it was really entrained in the soil on Mars. In addition to the ovens, we had a mass spectrometer, so it was kind of an instrument suite. So the gases, once you cook the material in the oven right here, the gases that come off there are directed to a mass spectrometer, which measures the mass to charge ratio of isotopes. In particular, it was designed to be sensitive to carbon, nitrogen, oxygen, hydrogen, neon, and so on, and also small hydrocarbon molecules. The other interesting thing about this, the instrument lead for this was Bill Boynton, and Bill was the lead for the gamma ray spectrometer on board the Mars Odyssey spacecraft. So Bill was in a relatively unique position that he made this discovery, or led this discovery, using his instrument from orbit, and then he gets to go off and build another instrument to go and verify his discovery on the ground. So it's pretty neat. Okay, we finally got to the launch pad in the summer of 2007, and we launched on August 4, 2007. We had a one-day delay due to some weather problems in the area, but fortunately it went off without a hitch. And then I'm going to show you a little animation here. About 10 months later, and 422 million miles, we approached Mars. We're going about 12,000 miles per hour right now, and we have to get down to 0 miles per hour in about 7 minutes. So we try to burn off a lot of that energy by entering the atmosphere and braking using an aeroshell. And the parachute deploys. We're going a couple hundred miles per hour right now. The aeroshell falls off, our lander legs deploy. Radar turns on, looks at the surface, gets an altitude measurement, and then we drop. Fortunately, our thrusters turn on, so these are those pulse thrusters, just going on and off very quickly. And then we pirouette to try to get the right orientation with respect to the sun for the mission. Minutes into the mission, all this stuff happens right here. So the solar panels deploy. The SSI pops up on its mast. Then the weather station pops up. The biobarrier bag deploys. Okay, so all that stuff happened in about 10 minutes after landing. The rest of these things happened over several sols. So we deployed the robotic arm. So now we're ready to go and acquire our first sample. So we take a look around, we pick a spot. Now we're grabbing the sample with the scoop, bring it over to the TIGA. TIGA door opens. We pour in the sample, start the Martian barbecue. Then we open the LiDAR door, and we start doing this laser ranging experiment. Yeah, I'll talk about that. The other thing I wanted to point out was this picture right here. Hopefully a lot of you have already seen it, particularly since we're all Mars aficionados here. But this was a picture taken of the Phoenix a few minutes before it actually landed on the Martian surface. This was taken from orbit by the HiRISE instrument on board another spacecraft. So the Mars Reconnaissance Orbiter is an orbit around Mars. It has this great camera on board called HiRISE, which is also run at the University of Arizona. And weeks in advance, they planned this out. They figured out where Phoenix was going to be entering the Martian atmosphere and commanded their camera to go ahead and try to take pictures of it as it was landing. And certainly that would have been important had we had a failure. Fortunately, we didn't, but it just created this really just awesome image, I think. So here's the lander right here at the bottom. This is the parachute, and you can almost make out the parachute lines. So this is the first time we'd ever done this around another planet. It was pretty neat. And it happened just a few minutes before we landed, so about 2 minutes. We landed at 7:38.